Hello friends, a very good morning to all the students. Am I audible to all the students? Okay, fine. Still the students are joining in the group. Okay, no issue. All the students are requested to mute their mics as well as off their videos and kindly join the meeting with the standard format which you are already aware of it. So dear friends, before starting with the discussion of the subject of basic mechanical engineering and the chapter that is the heat engines, since today that is the 1st January 2021, I wish all the students who have joined this particular group a very happy new year to all the students. And dear students, my best wishes to all of you that you become good practical engineers and do not become the theoretical engineers. Because dear friends, the market is looking for the practical engineers who are having very good practical knowledge and how they are solving the particular task given to them by applying the concepts they have studied. Okay, I am getting the responses from the students in the chat box. Okay, some of the students are also giving me the response of the Happy New Year. So thanks from my side. So dear friends, I hope now majority of the students have joined the meeting. So now I can proceed with my discussion of the subject that is the basic mechanical engineering. Dear friends, if you remember in the last lecture, we have started one of the important chapter of this subject. The chapter name that was the heat engines. So let me ask you some basic questions of the topics which were discussed in the last lecture. So any student can give me the answer in the chat box. What is the energy conversion in the heat engine? What is the energy conversion in the heat engine? Which energy is converted to which energy and finally to which energy? Try to understand the question and then answer me in the chat box. Respected students, I am mentioning the question very clearly, so there must not be any doubt in your mind. Understand the question perfectly. In the heat engines, which energy is converted to which energy? Okay, roll number 65 has given me the answer. Roll number 55 has given me the answer. Okay, so majority of the students are confused somewhat. Okay, so the answer which I was looking for, though some of the students has given me the perfect answer which I was expecting, during the operation of the heat engine, the chemical energy of the fuel is first converted to the heat energy or the thermal energy. And this heat energy or the thermal energy is again converted to the mechanical energy. So in the heat engines, there are two conversions. Try to remember, friends, these logics, these technical concepts are very important to be remembered and to be understood. First conversion is chemical energy into the thermal energy, and second will be the thermal energy into the mechanical energy. The mechanical energy you can also justify as the mechanical work. My next question to you, that is, from which component of heat engine the working fluid absorbs the heat? From which component of heat engine the working fluid absorbs the heat? Roll number 68 has given me the answer. Heat sink 65. Okay. Students, try to understand the question perfectly, because here I am getting the mixed responses from your side. My question is very specific. From which element of heat engine the working substance or the working fluid absorbs the heat? So the working fluid or the working substance will be absorbing the heat from the source itself, because the source is a high temperature reservoir. From that particular location, the working fluid will absorb the heat energy. And this absorbed heat energy working fluid is then transferred to the heat engine, or rather the converting machine, for producing the mechanical work. I hope you have understood what I am trying to justify. Is this concept clear to all? Kindly share your response in the chat box so that I can proceed further with current lecture. Okay friends, and if I am asking in which element the working fluid rejects the heat, in which element the working fluid rejects the heat, that now all the students must give me the perfect answer. Which is the component where the working fluid rejects the heat? Very good. 51, 54, 86. You have understood. 69 has also given me the answer. That is the cold temperature reservoir, and in technical we are knowing it as the sink. So now dear students, let us proceed in the current session. Now in this chapter of the heat engine, we will be studying the 4 different cycles of the heat engine. The first cycle that will be discussed in details in the current session, that is the Carnot cycle. So these are the different contents related to the Carnot cycle. First, we will understand the concepts of the Carnot theorem. Then we will understand the different processes in the Carnot cycle. Then we will make the derivation for determining the efficiency of the Carnot cycle. And finally, we will understand some of the important points related to the Carnot cycle. So let us proceed further. The first and the most important statement related to the mechanical engineering systems, mechanical components, or the engineering systems, that is the Carnot theorem. The Carnot theorem states that no cycle can be more efficient than a reversible cycle operating between the same temperature limits. That means, in simple terms, all our practical cycles will be less efficient than the reversible cycle. Repeating the Carnot theorem once again so that you are getting some important points out of it. The Carnot theorem states that no cycle can be more efficient than a reversible cycle operating between the same temperature limits. Dear students, now remember this point, the Carnot heat engine is a hypothetical engine, or it is also known as the ideal engine, because this engine it operates on the reversible Carnot cycle. And in this cycle, chapter number 1, we have understood the concept of the cycle. The initial and the final states must be the identical states. So the Carnot heat engine works on the reversible Carnot cycle, hence it is practically not possible. So the Carnot heat engine is considered as a hypothetical or the ideal engine. But remember one of the important point over here, that this cycle or the Carnot heat engine serves as the standard for measuring the performance of the different heat engines. And the different heat engines, they are operating between the two temperatures, and those two temperatures will be the high temperature and the cold temperature or the low temperature. So basically friends, the Carnot heat engine or the Carnot cycle gives us the benchmark or the reference point for determining the performance of our practical systems. Understand these points. We are going in now details related to the Carnot cycle and the Carnot theorem. Now friends, during the operation of the Carnot heat engine, Sadi Carnot, the German engineer, need to make some assumptions. And let me tell you, all the assumptions which are made by the Sadi Carnot, all the assumptions are the hypothetical assumptions. As I am explaining all the assumptions, you will be also understanding some of the points. Yes, sir, these are not the practical assumptions, they are the hypothetical concepts. When we relate these assumptions to the practical approach, there are some modifications, there are some bifurcations. So we need to focus on the assumptions which are made by the Carnot in the working of the Carnot engine, because they are used for the analysis of the Carnot engine. So let us discuss the assumptions one by one. The first assumption, that is the piston is moving in the cylinder, but it does not develop any friction during the motion. I hope you are getting my point, dear students. Whenever there will be the motion, always there will be the friction. If the friction is negligible, we are neglecting that friction. But in the assumption the Carnot has taken, that when the piston is moving in the cylinder, it does not develop any friction. And without friction, how the motion will be possible? I hope you are understanding the point. It is the hypothetical assumption. Kindly share your responses in the chat box if you are understanding this point. Okay, fine. So let us proceed further in the second assumption. So you will be getting some more idea of it. The next assumption, which was taken by Sadi Carnot, that is the walls of piston and cylinder are considered as the perfect insulators of heat. Now the perfect insulators also practically it is not possible, because if we are considering the perfect insulation, then this system will be the isolated system. Are you remembering all those points? Moving further, the transfer of heat does not change the temperature of source and sink. I expect that majority of the students will be laughing at the Carnot assumptions, because they are totally differing with the practical approach. The next fourth assumption, the working medium is a perfect gas. And the perfect gas will be having the constant specific heats. That means the perfect gas will be having the same value of the specific heat at constant pressure also, and it will be having the same value of specific heat at constant volume also. Dear students, are you understanding these points? Before starting the assumptions, I made my point perfectly clear that all these assumptions are hypothetical assumptions, but they were taken by Sadi Carnot. In practical, all these assumptions cannot be considered. I want the responses from other students also. If you are understanding the points, kindly share your responses in the chat box. Okay, 101 has responded to my comment, 56 has answered. What about the other students? Kindly share your responses so that I can proceed further with the discussion. Okay, fine. So now let us proceed further with the next assumption. The compression and the expansion processes are the reversible processes. Dear students, if you have understood the technical perspective of it, the compression and the expansion processes are totally both different processes. Or to be more specific, both are completely the opposite processes. In the compression, the volume decreases, but the pressure increases. Whereas in the expansion, the pressure decreases, but the volume increases. But in the Carnot, he has taken the assumption that the compression and expansion processes are reversible processes. And because of this assumption only, the Carnot engine is considered as the reversible heat engine. Now friends, let us proceed further and understand the several processes in the Carnot cycle. There are four main processes in this cycle. The first one, that is A to B, that is isothermal expansion process. The second one, that is B to C, that is adiabatic expansion process. The third one, that is C to D, isothermal compression process. And the final process D2A, that is the adiabatic compression process. And again we have reached to point number A. That means following all these four processes, I can tell that I have completed one cycle, because my starting point and the ending points both are identical. Let us understand all these four processes. The first process, that is isothermal expansion. This is the piston cylinder arrangement. This is the insulation which is being provided. Ideal gas is collected in the cylinder. During this process, at isothermal conditions, constant temperature conditions, the ideal gas is absorbing, receiving the heat from the source which is at temperature Th. And as the gas has received the heat, the energy of the gas is increased. This effect is passed on to the piston. So now the piston will be moving on vertical direction. So this process is taking place following the isothermal conditions. And as the piston is moving vertical direction because of the expansion, the pressure will be reducing, but the volume will be increasing. Remember, we are considering the volume and the pressures of the ideal gas, not of the cylinder. Let us proceed further with the second process, that is the adiabatic expansion process. Here, as you are seeing that the source is removed, and from where there was the heat transfer, now we are using the thermal insulation. So now the piston cylinder arrangement is perfectly insulated. There is no heat transfer, but still there is some heat energy with the ideal gas, which will be affecting the piston to again move in the upward direction. But in this case, since there is no heat transfer, we are considering as the adiabatic process, and the piston is still moving in the above direction, vertical direction. So still there is the expansion of the ideal gas. Dear students, very easy to understand. Just remember the main points, then you will be perfectly understanding the points. Have you understood both these processes? The isothermal expansion process and the adiabatic expansion process. Try to remember the concepts we have discussed already in the properties of gases related to the isothermal and the adiabatics, and the main concepts related to the expansion. Have you understood, all the students? Kindly share your responses in the chat box so that I can proceed further with the discussion of the processes. Okay, fine. Thank you all. So these two processes are clear, that is the isothermal expansion process, and second one, that is the adiabatic expansion. Now let us understand the third process. In this process, the name is isothermal compression process. Now the piston will be coming in the backward direction. So we are seeing that the piston is moving vertically downwards. So as the piston is moving in vertically downward direction, the ideal gas which is filled in the cylinder, that will be compressed in the cylinder. And because of this compression, whatever the energy developed in the ideal gas, that energy will be rejected to the heat sink. So that heat sink is maintained at the lower temperature, that is TL, and the energy rejected by the ideal gas, which is shown as QL. And now moving further to the last process, that is the adiabatic compression process. Still the piston is moving in the downward direction, but now in this case we have stopped the heat rejected to the sink, and in this sink we have installed or made the contact with the thermal insulator. So the heat transfer from the ideal gas to the sink is stopped. There is no heat transfer, but the compression process is still continued. So hence this process is known as the adiabatic compression process. And after this process, now the ideal gas has reached to its initial conditions. The piston has reached to its starting point, and again we have reached to this point. And this is again the starting point of the cycle. So the cycle will be starting from A, B, C, D, A, B, C, D. So this is the pattern in which the Carnot cycle will be following or operating. Let us understand this concept with the PV diagram so that it will be perfectly clear to you. This is the pressure volume diagram and the temperature entropy diagram. Entropy is represented as capital S. And dear friends, remember the entropy is constant during the adiabatic process since there is no heat transfer. The first process was the isothermal expansion. So because of the expansion, you are seeing that the temperature remains constant, but the pressure decreases, but the volume increases from V1 to V2. The second process was the adiabatic expansion. So again, the pressure is increasing from P2 to P3. Pressure is decreasing from P2 to P3, but the volume is increasing from V2 to V3. The temperature is now changed because when we are considering the third process, that is isothermal compression, we need to reject the heat to the sink. So that must be the sink at the lower temperature as compared to the source temperature. So now new temperature we have taken, that is T2. Then the compression process is taking place. In the compression, we are knowing that the volume is reducing, the pressure is increasing, and finally the adiabatic compression. And again, we have reached at point number 1. So using this diagram, understanding this diagram, I can tell that I have completed one cycle. The same can be represented on the TS diagram. 1 to 2, that is isothermal process, temperature remains constant. 2 to 3, adiabatic process, entropy remains constant. Again 3 to 4, isothermal compression, and 4 to 1, that is adiabatic compression. Dear students, have you remembered, understood up till this point? The same diagram is also given in your book, but I think some notations have been changed. In this, in book they have shown energy entering, that is Q1, and in this they have shown the energy leaving, that is Q2. Okay, so now let us proceed further and make the derivation of the efficiency of the Carnot cycle. You can start noting down the important steps of the derivation. It can be asked in your examination. The efficiency is defined as the ratio of work done by the working substance in one cycle to the amount of heat extracted from the source. Dear students, I am not using the notations which are used in your books. I am slightly using some different notations in order to explain you better. But you can understand this point, you can correlate this explanation with the concepts of your textbook, and then you can perfectly understand the textbook method. So standard equation for efficiency of Carnot engine, that is eta Carnot. Eta is the Greek symbol which is used for describing the efficiency. So eta Carnot or efficiency of Carnot, that is work done upon heat extracted by the working fluid. So that is W upon QH. QH was the amount of heat energy extracted by the working fluid from the source. So now work done is equal to amount of heat supplied minus the amount of heat rejected. Substituting this value in this equation, so eta Carnot is equal to 1. Eta Carnot is equal to W upon QH. So substituting the value of W, so that is QH minus QL upon QH. QH is common. So final equation number 1 we are getting, that is eta Carnot 1 minus QL by QH. Dear students, have you understood up till this point in the derivation? Very easy to understand. Just remember the main points, then the derivation will be perfectly clear. Have you understood up till this point, up till this equation? Eta Carnot is equal to 1 minus QL by QH. Okay, QL, that is the amount of heat rejected to the sink, and QH is the amount of heat received from the source. Let us proceed further in the derivation. So now applying the isothermal conditions for process 1 to 2 and process 3 to 4, because we are seeing in the PV diagram 1 to 2 and 3 to 4, that is the isothermal processes, and in the isothermal processes we are knowing W, that is equal to Q. Work done is equal to heat transfer because delta U is equal to 0. So work done, we are knowing the equation C ln V2 by V1. So in place of C, I can write down PV or MRT. So for QH, that is per process 1 to 2 energy entering in the engine or the cycle. So I will be writing QH is equal to MRTH ln the final volume divided by the initial volume. And similarly for the another process, that is 3 to 4 isothermal compression process, the same logic is applied. So QL, that is equal to MRTL ln V3 by V4. In order to justify the sign convections, remember friends, here I have changed the values so that I am getting the answer of QL. But in technical, when the heat is rejected, the sign comes out to be negative. I hope you are understanding these points. Now taking the ratio of QL by QH, MR, the common terms, so they will be cancelled it out. And finally, we are getting QL by QH is equal to TL into ln V3 by V4 divided by TH ln V2 by V1. Equation number A. Dear friends, are you understanding the derivation? See, the steps are somewhat different given in your book, but these are the main steps, the simple steps which you need to remember. In the book, only the labeling will be different, the notations will be different. Are you understanding all the students? Kindly give me the positive responses in the chat box, or if you are having any doubt, I can clear your doubt at this point, then we can proceed further. Okay, majority of the students has given me the confirmation. Thank you all. So you have understood the concept perfectly. Okay, so let us proceed further. Now we are considering the adiabatic processes. So for the adiabatic processes 2 to 3 and 4 to 1, we can write relationship between temperature and volume. So for process 2 to 3, we are using the equation T V raised to gamma minus 1 is equal to constant. So TH V2 raised to gamma minus 1, that is equal to TL V3 raised to gamma minus 1. And similarly for process 4 to 1, I can write down TH V1 raised to gamma minus 1, that is equal to TL into V4 raised to gamma minus 1. On dividing both the above equations, TH will be cancelled, TL will be cancelled. So we are getting this answer, V2 by V1 raised to gamma minus 1 is equal to V3 by V4 raised to gamma minus 1. Okay, roll number 67. The answer to your question is, if you are taking V4 by V3, then you will be getting the negative answer. Understanding the point? And if you are getting the negative answer, so in the work done, when I am doing QH minus QL, minus minus becomes plus. So I will be getting QH plus QL. That is the total work done, but I want to find out the work produced at the output. So I need to remove the losses. So in order to justify that sign convections, I have taken the ratio that is V3 by V4. Have you understood 67? Okay, fine. So on dividing above equations, V2 by V1 raised to gamma minus 1 is equal to V3 by V4 raised to gamma minus 1. Thus doing the mathematical calculations, raised to are the same. So both the raised to's are cancelled. So finally we are getting V2 by V1 is equal to V3 by V4, equation number B. Understood, friends, up till this point? Are you getting all the points? Are you noting down all the concepts? So substituting now the values of equation B in equation A, we'll be getting the answer, that is QL by QH is equal to TL by TH. Thus, the efficiency of the Carnot cycle, eta Carnot is equal to 1 minus QL by QH. So, eta Carnot is equal to 1 minus, substituting this value, that is TL by TH, where TL is the temperature of the sink and TH is the temperature of the source. TH and TL both must be expressed in the Kelvin scale. So this is the final answer of the Carnot cycle. The efficiency of the Carnot cycle derivation can be asked in your examination. You need to follow the steps mentioned in your textbook. But these are the simple steps in order to understand the logic and how we are getting the final answer. So friends, now let us proceed further to the final topic of this session, some of the important remarks related to the Carnot efficiency. So efficiency, as we are knowing that it is always less than 1 because TL is less than TH. This implies the efficiency cannot be 100%. It can be 1 or 100% only when TL is equal to 0 Kelvin. But 0 Kelvin, that is the absolute zero temperature, which is again impossible to attain practically. Rule number 65, you cannot write down this answer in the exam because the notations are different related to your textbook. You need to follow the standard textbook for preparing the answers for the examination. This is only for the remembering purposes, for clearing the steps of the derivation. The next important point is the efficiency of the Carnot engine is independent of the working substance, because in the efficiency equation we have not found anywhere the topic mentioned related to the working substance. So only the efficiency depends upon the temperatures of the source and sink. The greater the difference between the two temperatures, the higher will be the efficiency. Moving further, when both the temperatures are equal, that is TH is equal to TL, the efficiency comes out to be 0. So no engine can work having the source and the sink at the same temperature. The entire process of the Carnot heat engine is a reversible process. So the Carnot engine is itself a reversible engine and has the maximum efficiency. But all other practical heat engines, example the diesel engine, the petrol engine and the steam engine, are not the perfectly the reversible engines, and hence the practical engines, the petrol engines, diesel engines, the steam engines, all the engines, the practical engines, they are having the efficiency less than 100%. But theoretically, for understanding purposes, we can understand that the Carnot heat engine, since it is the reversible heat engine, the efficiency of the Carnot heat engine can be considered as the 100%. So dear friends, with this, I am concluding this session from my side. Thank you for watching this session. Have a nice day. Now friends, still we are having some few minutes left in the session. If you are having some doubts or the questions, you can ask me in the chat box related to the topics which I have discussed in the current session. All the topics are very important. Any topic can be asked in the GTU examination or the theoretical examination.